The search for reliable early biomarkers of Alzheimer's disease has been a defining challenge in modern neurology. By the time cognitive symptoms appear, confusion, memory loss, impaired reasoning, the underlying neurodegenerative damage is already extensive. Current diagnostic tools, such as amyloid PET imaging or cerebrospinal fluid analysis, while valuable, are either invasive, expensive, or fail to detect disease in its earliest, most reversible stages. This has prompted a growing interest in metabolic biomarkers, those that reflect subtle, preclinical disruptions in brain energy homeostasis. Among them, glycogen accumulation in brain cells, particularly astrocytes, is emerging as a surprisingly promising candidate. In a healthy brain, glycogen is present in only modest quantities, stored primarily in astrocytes as a tightly regulated reserve. It serves as an emergency fuel, mobilized during periods of high demand or glucose scarcity to supply neurons with lactate and other intermediates. But in Alzheimer's disease and related disorders, this balance begins to break down. Astrocytes in vulnerable brain regions, such as the hippocampus and cortex, begin to accumulate abnormal glycogen deposits. These may appear as overexpanded glycogen granules or even malformed structures akin to polyglucosan bodies, which are poorly branched and resistant to normal enzymatic breakdown. This shift suggests that glycogen metabolism becomes dysregulated early in the disease process, long before amyloid plaques or tau tangles reach critical mass. Several mechanisms could drive this buildup: impaired glucose uptake due to insulin resistance, chronic inflammation disrupting astrocytic enzyme function, or oxidative stress altering glycogen structure. As glycogen accumulates, astrocytes may lose their ability to efficiently support neurons, leading to local energy deficits, glutamate toxicity, and eventually synaptic failure. In this way, glycogen dysregulation may not just reflect disease, it may actively drive its progression. What makes glycogen particularly intriguing as a biomarker is its detectability. While traditional brain glycogen measurement required post-mortem analysis, advances in magnetic resonance spectroscopy, MRS, and metabolomics are making it increasingly possible to monitor glycogen content in vivo. High-field MRS, especially using carbon-13 or phosphorus tracers, can now detect regional changes in brain glycogen levels with reasonable spatial resolution. Studies in animal models have already demonstrated that glycogen buildup precedes behavioral symptoms and correlates with other metabolic dysfunctions. Human trials are still in their infancy, but as imaging sensitivity improves, glycogen quantification may become a feasible, non-invasive tool for early diagnosis. Beyond imaging, metabolomic profiling of cerebrospinal fluid or blood could reveal biomarkers related to glycogen metabolism, such as altered levels of glucose, 6-phosphate, lactate, or enzymes like glycogen synthase and phosphorylase. These could serve as indirect indicators of astrocytic dysfunction and be incorporated into multimodal diagnostic panels. Combined with genetic risk markers like APO4 or with digital cognitive tracking, glycogen-related metabolites may help identify high-risk individuals years before cognitive decline becomes irreversible. Still, caution is warranted. Not all glycogen accumulation is pathological. The brain normally increases glycogen stores after sleep deprivation, learning, or physical exertion. Therefore, diagnostic accuracy will depend on establishing disease-specific patterns of accumulation by region, timing, and structural form. Additionally, individual variability in metabolic health, diet, and insulin sensitivity could influence glycogen levels, making standardization of measurement techniques and interpretive frameworks essential. But the potential upside is substantial. A biomarker that detects Alzheimer's progression early, while patients are still cognitively intact, could transform treatment strategy. It would enable timely lifestyle interventions, enrollment in clinical trials, or even future metabolic therapies designed to restore glycogen cycling in astrocytes. More importantly, it reframes Alzheimer's not just as a disease of misfolded proteins, but as a disease of energy imbalance, a breakdown in the cellular systems meant to sustain the brain's most fundamental operations. In this light, glycogen accumulation is not merely a bystander or a consequence of neurodegeneration. It may be a signpost, pointing to the first cracks in the brain's metabolic infrastructure. Tracking it through imaging, biochemistry, or both could give us a precious head start in a disease where time is everything. And in doing so, It might help shift the Alzheimer's narrative from one of late-stage loss to one of early, actionable warning.